Uh, okay, guys, this is Madhav, and today we are going to discuss about Splay Tree in data structures. So today we are going to discuss about Splay Tree, and then let's just get into the topic. So basically, Splay Tree is not different from any other trees like binary tree or red white trees or anything like that. So binary tree is almost similar to the splay tree. So the splay trees are self-balancing or self-adjustable binary search trees. So it is not so different. But you may just get it out then what is the use of the splay tree if these things are related or sorry these things are similar to each other, then what is the use of the splay tree? So basically the time complexity of binary tree is not so efficient than not efficient than that of the splay tree. So that is the very basic main thing for finding the splay tree. So the time complexity is the major reason. So what is time complexity? So time complexity of a binary search tree is for an average case big O of log n, and for worst cases big O of n. So this is a time complexity for a binary search. So now we can just say like splay trees are not strictly balanced trees, but they are just roughly balanced trees because uh, in this splay trees we also perform some rotations which are almost similar to that of AVL tree. So it is almost similar to that of AVL trees. So it is also similar to binary trees. So these are these are the rotations in which we perform during the insertion if we need to just find. So basically splay tree is one of the major tree which is used for only for the searching purpose. So this is one of the major reason for finding a splay tree. So searching is more efficient in a splay tree. So okay, let us just work on these values in the splay tree. So let me just copy this splay tree and just I will just paste it in the page. So yeah, now we need to just search for this element seven. So basically, where is element seven? So element seven is in the place of root node's left position. So basically, we need to just clear one thing. So Splay tree, as I said before, it is almost use it for the searching purpose. This is because if we need to just search one of the element in this tree, so the process is we will just bring this node to its head position by using this rotations, and then we will just perform our search operation so that we can just find that element at its head position. Then with this, we can say that the time complexity may reduce with the help of this splay tree. So now we need to just find out this seven position. So we need to just find out the seven element. So to perform this, first we need to just do right rotation. So this is zigzag rotation. So as we had said before in this slide, so first it is zig rotation, right rotation. So if we just perform a right rotation, then it will just become like this. So it will just move like this. And then here we can just see the ninth element, and here we can just see this ninth element, and then it will just join to its left position as it is less than 10, so it will be to its left position, and the remaining will just come to its head position. So if it is just coming to its head position, then we can just say like so 7 is in its head position. Let me just bring you the old one so that if we just perform this, 7 will just come to this position. So if it is in this position, so we can just find out the element which is efficient. So let me just draw this. It's not a problem. So okay, 7 will come to this position, and then 10 will just, so 7 will just come to this position, and then 10 will move to its right side. So if we just move to its right side, then the element at 9 will join to its left position of 10, and then the tree will just balance it. So it is just roughly a binary search tree. So it is even agreed if we do not follow all the binary search conditions. So first thing is completed, and the second one is 1. So if we need to just find the position of 1, what we need to do? So this is zigzag rotation. So we need to just perform two right operations. That is, if we just take this whole thing to the another side, and then the ninth position again will join to its 10, and then again if we just bring this the whole thing, so it will just come here, and the 7 will become the node, and this whole thing will join here. So if we just complete like this, and then we need to just perform another rotation, so that 7 will just move here, and then 1 will come to its top position, and so it is not having any child, so the other elements will not just move to that side, as we had done for the case of 9. So let me just perform this with the help of a normal thing. So here now it is 10, and it's 7, and it's 15. So we will just move this position like this, and then after moving this like this, so here we are having an element like 9, so it will just move to its left position, and then finally it's 1, so it will become this root node, so that if we just find the things, so it's, let me just write 7 and 10 and then 15 and then 9. So like this we will just swap those elements. This is a zigzag rotation. So with the help of this we will just find out the zigzag rotation, and then next coming to this, we need to just find out the value of 20, which is at right side right, that is which is at this position. So like this we will also just move this to this side, so that it will just become like this. So let me, sorry, this 13 is belonging to 15. So okay, if we just move like this, then this 15th position will become to its right side. So it will just become to its right side. And then if it is at its root position, then we need to just maintain like this. And then if we just like to just we can just make this. So if we just make to its top position, and then if we can just make to this root node, so this will become root. So if we just search for 20, then we can just find the element, as I had explained before. This is zag rotation, I think so. And then if we just find 13, so here now we need to just find out the element 13, which is here. So we need to perform a left operation, and then we need to just perform I think we need to just perform this left operation, and then with this we will just bring this 13 element to its right, and then we need to just perform our right operation. I think this is zigzag rotation, so we need to just perform like this to bring the element. So I will just show how to do this. So basically, if we just try to perform this right operation, then we can just say like the child in its 13 will just reach to its top position. So here we will just remove like this, and then 13 will come to its top position, and then the remaining will be like this same. And then we can just perform a left operation, so that 13 reaches to its top position, and then it will just do like this. So we will just perform a write operation, and then we will just bring out this chain node to its real position, and then we will just perform a left operation. Then this whole thing will happen, and then 13 will be to its root position. So we perform both the operations. Then we can just make this 13 at its root position. So by performing this rotations, we can just get those root nodes to its heads position, and we can just make this coding efficient for searching to find out the element which is at the head position. So this is about Splay Tree. Thank you for watching.